right now, humanity's fastest spacecraft is screaming through space at 430,000 miles per hour. That sounds impossibly fast until you realize it would still take 6,000 years to reach the nearest star. So here's the question. Nobody's really answered honestly. How far could a human being actually travel through space before they die? Not in theory. Not with magical future technology we haven't invented yet, but with real physics, real engineering, and the brutal constraints of a human lifespan. Because the answer is way more interesting than you think. Let's start with what we've actually done. Voyager 1 launched in 1977, back when the average computer had less processing power than your microwave. It's now 15.9 billion miles from Earth, traveling at about 38,000 miles per hour. That makes it the most distant human-made object in existence, and it's barely left the neighborhood. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. At its current speed, Voyager 1 will take nearly 20,000 years to travel just 1 light year. The nearest star system, Alpha Centauri, sits 4.24 light years away. Do the math, and Voyager won't get there for roughly 80,000 years. That's not a journey. That's geological time. Need food, water, oxygen, radiation. Need food, water, oxygen, radiation shielding, and enough psychological support to prevent someone from losing their mind in the endless black. Everything changes. The fastest we've ever moved a spacecraft designed with human missions in mind tops out around 25,000 miles per hour. That's the Apollo missions returning from the moon. Impressive by Earth standards, laughable by cosmic ones. At that velocity, a trip to Mars takes 6 to 9 months. Not to another star, to the next planet over. Mars orbits the Sun at an average distance of 140 million miles from Earth. On a good day, when the planets align just right, that drops to about 34 million miles. Chemical rockets, the kind we've relied on since the 1960s, can make that journey in roughly 9 months, using what's called a Hohmann transfer orbit. It's the most fuel-efficient path, but it's slow, agonizingly slow. And here's the thing nobody mentions in those glossy Mars colonization videos. 9 months out, 16 months waiting for the planets to realign. 9 months back. That's 34 months total. Nearly 3 years for a round trip to our closest planetary neighbor. Your body starts breaking down after just a few weeks in zero gravity. Bones lose roughly 1% of their mass every month. Muscles atrophy. Your cardiovascular system forgets how to pump blood against gravity. Astronauts on the International Space Station exercise 2 hours every single day just to slow the decay. Even then, they come back weaker. Radiation is worse. Earth's magnetic field shields us from charged particles screaming through space at near light speed. Step outside that protective bubble and you're exposed to galactic cosmic rays, solar particle events, and a constant bombardery of high-energy radiation that tears through your cells like invisible bullets. NASA calculated that a Mars round trip using conventional 9-month trajectories would expose astronauts to 0.66 sieverts of radiation. The agency's career limit for astronauts is 1 sievert total. One Mars mission would burn through 2/3 of that allowance. So before we even talk about reaching the stars, we're struggling to safely reach the next planet. The human body wasn't designed for space. It was designed for 1 g of gravity, a thick atmosphere, and a magnetic shield that's been protecting life for billions of years. But let's say we solve those problems. Better shielding, artificial gravity through rotation, advanced life support systems. NASA recently outlined trajectories that could cut Mars travel time down to 90 days using SpaceX's Starship with multiple orbital refuelings. 90 days instead of 9 months. That's a massive improvement for radiation exposure and bone loss. Still, it requires 15 separate refueling missions in Earth orbit before departure. 15 launches just to gas up one ship. Chemical propulsion has limits. You can only make the fuel burn so efficiently, only generate so much thrust before the rocket equation defeats you. Every kilogram of payload requires exponentially more fuel, which adds weight, which requires more fuel, which adds more weight. It's a vicious cycle that puts hard caps on how fast and how far we can go. That's why engineers started thinking about nuclear power. Nuclear thermal propulsion heats hydrogen to extreme temperatures using a fission reactor instead of chemical combustion. The exhaust velocity doubles compared to conventional rockets. Double the exhaust velocity means you can cut travel time in half or carry twice as much cargo. Mars in 45 days instead of 90. Suddenly, the radiation problem becomes manageable. Nuclear electric propulsion takes a different approach. Use a reactor to generate electricity, then accelerate ionized gas through electromagnetic fields. The thrust is tiny, barely enough to feel, but it's incredibly efficient and can run continuously for months or years, perfect for cargo missions where time isn't critical. Less ideal for humans who need to minimize radiation exposure. NASA's working on both systems with a goal of getting crew travel time between Earth and Mars down to 2 years total. Not 2 years each way. 2 years for the entire mission, including surface time. That would make Mars trips comparable to long-duration stays on the International Space Station, something we know humans can survive. But we're still talking about Mars, a planet in our own solar system. What about everything else? What about the stars? This is where the numbers become almost offensive. Proxima Centauri, that nearest star at 4.24 light-years, is 25 trillion miles away. With current chemical rockets, the journey takes 80,000 years. Nuclear thermal propulsion might cut that to 40,000 years. Still completely impossible for human travel. You need something radically different, something that doesn't just improve on chemical rockets, but operates on entirely different physics. Enter fusion propulsion. Fusion is what powers the sun. Slam hydrogen atoms together with enough force, and they fuse into helium, releasing tremendous energy. We've been trying to harness controlled fusion for decades. The engineering challenges are immense. You need to contain plasma at temperatures hotter than the sun's core. Maintain that containment long enough for fusion to occur, and extract more energy than you put in. Several projects are getting close. The direct fusion drive concept could theoretically propel a 1,000 kilogram spacecraft to Pluto in 4 years. Pluto sits roughly 3.6 billion miles from Earth. Chemical rockets would take a decade or more. Fusion cuts that to 4 years by maintaining constant acceleration building up velocity gradually but relentlessly. Scale that up for human missions, and fusion starts looking genuinely transformative. A crewed spacecraft to Mars in 90 days instead of 9 months. To the outer planets in years instead of decades. But even fusion, as revolutionary as it would be, doesn't crack the interstellar barrier. It makes the solar system accessible. The stars remain out of reach unless you're willing to think even more radically. Antimatter propulsion has an energy density of 9 times 10 to the 16th joules per kilogram. That's matter and antimatter annihilating each other with 100% conversion to energy. Nothing in the known universe releases energy more efficiently. A millionth of a gram of antimatter could fuel a 1-year trip to Mars. Beam core antimatter rockets could theoretically reach 40% the speed of light. At that velocity, Proxima Centauri becomes a 10-year journey, still a significant chunk of a human lifetime, but actually doable. The problem is, we can't make antimatter in useful quantities. CERN's antiproton decelerator produces about 10 nanograms per year at a cost of several $1 million. Scaling that up to even a single gram would require 25 million kilowatt hours of energy. We're talking about technology that's theoretically possible, but practically centuries away from implementation. So here's where we actually stand. Mars is achievable with current or near-term technology, but it pushes human endurance to the limit. The outer solar system becomes accessible with fusion, maybe within a few decades if development continues. But the nearest stars? With conventional approaches, even antimatter propulsion, you're looking at journeys measured in decades at minimum. That's assuming you could survive the trip. Remember, we're not just talking about propulsion. Every day in space, your body deteriorates. Radiation accumulates in your cells. Psychological isolation builds. You need closed-loop life support that can recycle everything perfectly for years or decades. One critical failure and everyone dies. The fastest humans have ever traveled was during Apollo 10's return from the moon. The crew hit 24,791 miles per hour relative to Earth. At that speed, crossing the distance to Proxima Centauri would take 115,000 years. Even if we match the Parker Solar Probe's record-breaking 430,000 miles per hour, we're still looking at 6,300 years. You start to see the problem. The universe is too big. The distances are too vast. The speeds required are too extreme, and the human body is too fragile. But there's something we haven't talked about yet. Something that changes the entire calculation in ways that seem impossible, but are absolutely real. Because when you start moving at significant fractions of light speed, the universe itself starts behaving differently. Time stops being absolute. Space contracts. And suddenly, journeys that should take thousands of years become achievable within a single human lifespan. Not through better engines, through physics that Einstein figured out over a century ago. But that still sounds like science fiction. The faster you move, the slower time passes for you relative to everyone else. It's called time dilation, and it's not speculation, it's measured reality. Astronauts on the International Space Station, orbiting at 17,500 miles per hour, age about 0.005 seconds slower than people on Earth during a 6-month mission. Completely negligible, but ramp that velocity up to significant fractions of light speed, and the effect becomes dramatic. At 95% light speed, time slows down to about 1/3 its normal rate. An astronaut traveling at that velocity for 10 years by their own clock would return to find 32 years had passed on Earth. Their twin would be 22 years older. Push it further. At 99.9% light speed, time dilation increases by more than 22 times. 1 year for the crew equals 22 years for everyone else. Suddenly, you can cross distances that would normally take decades or centuries while only aging a few years yourself. This opens up possibilities that sound insane, but follow directly from proven physics. With a ship capable of constant 1g acceleration, matching Earth's gravity and solving the bone loss problem simultaneously, you could reach the edge of the observable universe and return within a single human lifetime, by your clock anyway. Billions of years would pass on Earth, but you'd only age 40 or 50 years. The catch, and it's a massive one, is building an engine capable of that kind of sustained acceleration. We're not even close, but the physics allows it. That's what makes this more than fantasy. The universe itself permits human beings to travel cosmic distances within their natural lifespan. We just need to figure out the engineering. And that's what makes the question so fascinating. How far can humans actually travel in one lifetime? The answer depends entirely on what technology you're using and what reference frame you're measuring from. Let's start with the most accessible option, Mars. Right now, with traditional chemical rockets following a Hohmann transfer orbit, getting to Mars takes between 6 and 9 months. That's the reality NASA has been working with for decades. Launch when Earth and Mars are properly aligned, coast through space for most of the journey, arrive exhausted and radiation exposed with your bones slightly less dense than when you left. The round trip. Almost 3 years. 9 months there. 16 months waiting for the planets to realign. 9 months back. That's if everything goes perfectly and nobody dies from equipment failure, radiation poisoning, or the psychological breakdown that comes from being trapped in a tin can with the same 5 people for 34 months. But that timeline is already outdated. NASA recently demonstrated something most people don't know about. Using SpaceX Starship with multiple orbital refuelings, they've outlined trajectories that cut Mars transit time down to 90 days, 3 months instead of 9. The catch is, you need roughly 15 refueling missions in low Earth orbit before departure. 15 separate launches just to top off your tanks before the actual journey begins. Why does this matter? Because radiation exposure scales with time. The Mars Science Laboratory measured 0.66 sieverts of radiation during its cruise to Mars, using the traditional 9-month trajectory. NASA's career limit for astronauts is 1 sievert total. A round trip using old methods would essentially end your career and significantly increase your cancer risk. Cut that to 90 days each way, and suddenly you're within safe limits. Your bones lose less density. You need less food, less water, less oxygen. The ship can be smaller, lighter, cheaper. 3 months is psychologically manageable in ways that 9 months isn't. That's the near-term reality. Chemical rockets optimized to their theoretical limits can get humans to Mars and back within 6 to 7 months of actual travel time. Add the surface stay, and you're looking at roughly 2 years total mission duration, which means in a single human lifetime, using technology that exists right now, you could potentially make multiple trips to Mars. Not comfortably, not safely by any reasonable standard, but physically possible. Now let's talk about what happens when we upgrade the engine. Nuclear thermal propulsion has been theoretically viable since the 1960s. The concept is straightforward. Instead of burning chemical fuel, you use a nuclear reactor to heat hydrogen propellant to extreme temperatures, then expel it through a nozzle. This gives you roughly twice the specific impulse of chemical rockets, meaning you get twice the velocity change from the same amount of propellant. NASA's current goal with nuclear thermal propulsion is to cut Mars mission duration down to about 2 years total. That includes transit time both ways and surface operations. More importantly, the increased efficiency means you can carry more supplies, more equipment, more radiation shielding. But nuclear thermal is just the beginning. Nuclear electric propulsion takes a different approach. Instead of heating propellant directly, you use a reactor to generate electricity, then use that electricity to accelerate ions to extremely high velocities through an electric thruster. The thrust is lower, but the efficiency is phenomenal. These systems can run continuously for years, gradually building up to velocities that chemical rockets can't touch. The problem with nuclear electric is that low thrust. For crewed missions where you want to minimize radiation exposure and bone loss, you need to get places relatively quickly. Nuclear electric is perfect for cargo missions, where you can spend years slowly accelerating a massive payload, but less ideal when humans are involved. That's where fusion propulsion enters the picture. Fusion represents a potential game changer because it offers both high thrust and high efficiency. A fusion-powered spacecraft could theoretically reach Mars in 90 days or less, while using a fraction of the fuel required by chemical or nuclear thermal systems. The direct fusion drive, currently in development, could propel a 1,000-kilogram spacecraft to Pluto in 4 years. Pluto, in 4 years. To put that in perspective, New Horizons took 9.5 years to reach Pluto, using a gravity assist from Jupiter. Fusion propulsion would more than double that speed, while carrying significantly more mass. The technology is real enough that static tests are scheduled to begin this year, with an orbital demonstration planned for 2027. We're not talking about far future speculation. This is engineering that's happening right now. But fusion still keeps us locked within the solar system for practical human travel. Even at those speeds, reaching Proxima Centauri would take centuries, multiple human lifetimes, which is why some researchers have started exploring something that sounds completely insane until you look at the physics. Antimatter. When matter meets antimatter, they annihilate each other with 100% efficiency, converting all their mass directly into energy, according to Einstein's equation. The energy density is unmatched by anything else in physics. 9 times 10 to the 16th joules per kilogram. That's orders of magnitude beyond anything chemical, nuclear, or fusion can achieve. A beam core antimatter rocket could theoretically reach 40% light speed. At that velocity, you could reach Alpha Centauri in about 11 years, Proxima Centauri in less than that. Within a single human lifespan, you could visit another star system and potentially return. The amount of antimatter required is surprisingly small. For a one-year trip to Mars, you'd need roughly 1/1,000,000th of a gram. The problem isn't the quantity needed, it's the production. CERN's antiproton decelerator produces about 10 nanograms of antiprotons per year at a cost of several $1,000,000. Producing a single gram of antimatter would require roughly 25 million kilowatt-hours of energy and an amount of money that makes government defense budgets look reasonable. Even if we solved the production problem, storage is nightmarish. Antimatter annihilates on contact with normal matter, so it has to be contained using electromagnetic fields in a perfect vacuum. Any containment failure means instant catastrophic explosion. But let's say we figure it out. Let's say 100 years from now, we've cracked efficient antimatter production and reliable magnetic containment. What happens when you start pushing towards significant fractions of light speed? This is where Einstein's predictions stop sounding like abstract physics and start becoming the only thing that makes interstellar travel possible. Time dilation becomes noticeable around 80% light speed. Below that, the effects exist, but they're minimal. Above that threshold, things get weird fast. At 95% light speed, time for the crew runs at about 1/3 the rate of time for everyone back on Earth. Travel for 10 years by your clock, and 32 years pass at home. Your twin brother is now 22 years older than you. Push it to 99.9% light speed, and the dilation factor jumps to 22. 1 year for you equals 22 years for Earth. You could travel to a star 100 light years away, spend what feels like a few years exploring, return home, and find that centuries had passed. This isn't speculation. Time dilation is measured reality. We see it in particle accelerators every day. Moons created in cosmic ray collisions high in the atmosphere shouldn't be able to reach the ground before decaying. But they do because they're moving fast enough that time runs slower for them. From their reference frame, the atmosphere is contracted to a much thinner layer than we measure. The exact same physics applies to spacecraft. Move fast enough, and the distance to your destination literally contracts from your perspective while time slows down. The trip that takes 100 years from Earth's viewpoint might only take 5 years from yours. There's a theoretical calculation that borders on philosophical. If you had a ship capable of constant 1g acceleration, matching Earth's gravity and solving the bone loss problem, you could reach the edge of the observable universe and return within about 40 years, ship time. Billions of years would elapse on Earth. The sun would die. The galaxy would evolve beyond recognition. But you'd only age 4 decades. The engineering required is so far beyond anything we can currently build that it might as well be magic. But the physics allows it. That's the crucial distinction. These aren't fantasies that violate known laws. They're extreme applications of principles we've already confirmed. Which brings us back to the original question with a more nuanced answer. How far can humans travel in one lifetime depends entirely on whose lifetime you're measuring. From Earth's perspective, interstellar travel might take thousands of years even with advanced propulsion. But from the traveler's perspective, relativistic speeds make almost any destination theoretically reachable within a single human lifespan. The real barriers aren't physics. They're engineering, economics, and the question of whether anyone would volunteer for a journey that would separate them from everything and everyone they knew by an unbridgeable gulf of time. Because even if you could reach another star and return within your lifetime, everyone you left behind would be dead. Your entire civilization might have risen and fallen. You'd return as a time traveler from the past, carrying knowledge and memories from a world that no longer exists. That's the hidden cost of relativistic travel that nobody talks about. So what if you refused to accept that trade? What if the goal wasn't reaching another star yourself, but ensuring humanity reached it eventually? Enter the generation ship. The concept is straightforward in theory and nightmarish in execution. Build a vessel large enough to sustain a complete ecosystem. Load it with enough people to maintain genetic diversity. Accelerate it to a fraction of light speed using whatever propulsion technology you can manage. Then accept that everyone who boards will die long before arrival. Their children will die. Their grandchildren will die. Somewhere between 5 and 10 generations down the line, their descendants might see a new world. Project Hyperion represents the most detailed attempt to actually design such a vessel. Launched in 2011, the study aimed to assess whether crewed interstellar flight using current and near-future technology was even theoretically possible. Their baseline scenario involved a 250-year journey to a nearby star system, with the ship carrying between 500 and 1,500 people, depending on various design parameters. The numbers tell a sobering story. Using propulsion methods that are technologically feasible today, reaching Alpha Centauri would take somewhere between 1,000 and 81,000 years. Even with optimistic assumptions about future nuclear or fusion drives, you're looking at centuries minimum. The ship would need to travel at least 1.5% of light speed to make the trip in anything less than a millennium. That velocity creates its own problems. At one point, 5% light speed, a single grain of sand hitting the hull releases energy equivalent to a hand grenade. Interstellar space isn't truly empty. Hydrogen atoms, dust particles, the occasional larger debris all become kinetic kill vehicles at those speeds. Your ship needs shielding thick enough to survive constant bombardment for centuries. Then there's the life support challenge. Every human breathes roughly 550 liters of oxygen per day. They produce carbon dioxide, metabolic waste, heat. Multiply that by 1,000 people over 250 years, and you're talking about processing billions of liters of air, millions of tons of water, decades worth of food production. Nothing can fail. There's no resupply mission, no rescue if the recycling systems break down. The ship needs to be completely self-sufficient, capable of manufacturing spare parts, growing food, recycling waste with near-perfect efficiency for longer than the United States has existed as a nation. One major system failure and everyone dies. Unlike a Mars colony or lunar base, there's no aborting back to Earth. You're a quarter millennium away from help traveling at 4,500 kilometers per second. But the engineering challenges pale compared to the social ones. Imagine being born on a generation ship. You never chose this mission. Your great-great-grandparents made that choice. You've never seen Earth, never felt rain or breathed unfiltered air. Your entire universe is a metal tube hurtling through darkness. The destination star is just a bright point ahead, no closer than it was when you were born, no closer than it will be when you die. What keeps you motivated? What gives your life meaning when your entire existence serves a goal you'll never see achieved? The original crew had purpose. They volunteered, understanding the sacrifice. But what about Generation 3? Generation 7? Do they maintain the same dedication to a mission they inherited? History suggests that isolated populations develop their own cultures, their own priorities. What happens when Generation 5 decides the mission is pointless and they'd rather slow down and colonize some random asteroid? There's no authority structure that could prevent mutiny across that timescale. You can't rule by force when the descendants of your security team might decide they don't care about the original mission parameters. Project Hyperion estimated you'd need between 500 and 1,500 people, minimum, to maintain genetic diversity and preserve technical knowledge. That's large enough for significant social complexity. Factions form. Disagreements emerge. Resources become contested. You're essentially trying to maintain a stable civilization inside a sealed container for longer than most civilizations on Earth have lasted. And you have to preserve technical knowledge across that gap. The people who arrive need to understand systems designed by engineers who died 200 years earlier. They need to maintain fusion reactors or antimatter containment or whatever exotic propulsion system got them there. One generation fails to properly train the next, and critical knowledge evaporates. The ship keeps flying, but nobody understands how to fix the engines. Then there's the question of what they're flying toward. The ship launches based on observations made decades before departure. By the time it arrives, is the target planet still suitable? Did the precursor probe that was supposed to terraform it actually succeed? Is there some hostile alien presence that destroyed the probe and is now waiting for the colonists? You're committing 1,000 people and their descendants to a one-way journey based on information that will be centuries out of date by arrival. There's no turning back, no calling home for advice. You arrive at the destination and deal with whatever you find or die trying. These aren't unsolvable problems, but they're also not the kind you can prototype. You can't do a test run of a 250-year mission. Either your systems work for the full duration, or they don't. Either your social structure remains stable across 10 generations, or it collapses. You won't know until it's too late to fix. Which brings us to the alternative that sounds like science fiction, but is actually being seriously researched. What if the crew didn't have to stay awake? Human hibernation, induced torpor, cryogenic sleep. Whatever term you prefer, the concept is the same. Slow down human metabolism to the point where weeks or months pass in what feels like days. reduce the crew's resource requirements, eliminate the psychological stress of decades in a metal box, skip over the boring parts of the journey. We're not talking about freezing people solid like in the movies. That doesn't work because ice crystals rupture cells. Current research focuses on therapeutic hypothermia, lowering body temperature by just 5 to 7 degrees Celsius. At that temperature, metabolic rate drops significantly, heart rate slows, oxygen consumption decreases. The body enters a state similar to what bears do during winter. NASA has already developed chambers that can maintain this state for up to 2 weeks. SpaceWorks Enterprises is working on extending that to months for Mars missions. The idea isn't continuous hibernation for years, but cycling. Sleep for a few weeks, wake up for a few days, return to torpor. Stack enough cycles together and you could sleep through most of a multi-year journey. The benefits are enormous. An astronaut in torpor needs maybe 70% less food and oxygen. They produce less waste. The ship can be smaller because you don't need as much living space. Smaller ship means less mass to accelerate, which means less fuel required, which compounds the mass savings. A Mars mission that might need a 50-ton habitat for an awake crew could potentially use a 20-ton torpor module instead. More importantly, the psychological burden vanishes. You're not spending 3 years staring at the same walls going slowly insane. You fall asleep near Earth and wake up at Mars. Subjectively, the trip takes a few weeks instead of years. The isolation, the monotony, the crushing boredom that might be the real limiting factor for deep space missions all disappear. But torpor isn't magic. It doesn't stop aging. You still get 3 years older on a 3-year mission. You're just unconscious for most of it. Animals that hibernate do tend to live longer relative to their size, possibly because reduced metabolism means less cellular damage over time. Whether that translates to humans remains unknown. There are medical concerns too. Hibernating animals don't experience significant muscle and bone loss despite months of inactivity. Humans lose bone mass at roughly 1% per month in zero gravity, even with exercise. Would torpor prevent that? Make it worse? We don't know. Blood clots are another risk. So are infections. Cognitive effects after extended torpor are completely unexplored territory. And here's the problem. You can't really test this on Earth. The longest anyone has been kept in therapeutic hypothermia is a few weeks. Scaling that to months or years involves risks we can't quantify without actually doing it. The first people to attempt long-duration torpor will be guinea pigs, whether they like it or not. Still, for missions within the solar system, torpor might be the breakthrough that makes crewed exploration practical. Mars in 3 months of subjective time instead of 9 months awake. The outer planets without the crew going insane from isolation. Even generation ships become more feasible if you can sleep through the boring centuries and wake up for the interesting parts. But torpor doesn't solve the fundamental problem of interstellar distances. Even at 10% light speed, which is wildly beyond current capabilities, Alpha Centauri is 43 years away. You'd need to remain in torpor for 4 decades straight. The medical risks compound with duration. Equipment failures become more likely. You're betting your life that systems designed to keep you alive will function perfectly for half a century with nobody awake to fix problems, unless you combine approaches. Generation ship with torpor capability. Most of the population sleeps, while a small rotating crew stays awake to maintain systems. You still need the large vessel for genetic diversity and redundancy, but your resource requirements drop dramatically. The crew rotation prevents any one generation from bearing the full psychological burden, or you take it further. Build a ship, but don't put humans on it. Send frozen embryos with artificial wombs programmed to gestate them on arrival. Raise the first generation with robots and AI. By the time they're adults, you have a colony population with no memory of Earth, no nostalgia for home, just whatever life they've built on a new world. That raises ethical questions that make the technical challenges look simple. Is it moral to create people whose entire existence serves a purpose they didn't choose? Who raises these children? What kind of psychological development happens when your only parent is an AI? What happens if the AI malfunctions or the children reject the mission programming? These aren't hypothetical concerns anymore. The technology to attempt some version of this might exist within decades. The ethics haven't caught up. So maybe we need to be looking at this from a completely different angle. Forget putting humans on the ship at all. There's a concept called von Neumann probes, self-replicating machines that travel to other star systems, use local materials to build copies of themselves, then send those copies to even more stars. You seed one probe into the galaxy, and exponential mathematics does the rest. Within a few million years, every star system could be explored without risking a single human life. The idea dates back to the 1940s, when mathematician John von Neumann was working on the theory of self-replicating machines. Apply that to space exploration, and you solve multiple problems simultaneously. No life support, no food or water, no radiation shielding for fragile biology. The probe doesn't care if the journey takes 1,000 years, because it doesn't age or get bored or go insane. Each probe carries instructions for building more probes, plus all of humanity's accumulated knowledge. When it arrives at a new star system, it surveys the planets, analyzes the resources, and starts mining asteroids to construct copies of itself. Those copies launch to neighboring stars. The original probe stays behind to continue gathering data and transmitting it back to Earth. The data transmission is the bottleneck. Even traveling at light speed, information from a probe at Alpha Centauri takes over 4 years to reach us. A probe at a star 100 light-years away needs a century just to send a single message home. You're not exploring in real time. You're creating an archive that future generations will access. But here's what makes this concept genuinely possible with current technology. We've already built machines that can survive decades in space. Voyager 1 and Voyager 2 have been operational for nearly 50 years. We've landed rovers on Mars that functioned for years beyond their planned missions. We've demonstrated asteroid mining techniques and in situ resource utilization. The missing piece is the self-replication, building a factory that can process raw materials into complex electronics and mechanical systems without human supervision. We can do parts of this on Earth with automated manufacturing, but scaling it to work with asteroid regolith and random minerals in an alien star system is an engineering challenge that hasn't been solved. There's also the contamination question. Send self-replicating machines into the galaxy, and you're potentially spreading Earth origin technology to every habitable world. What happens when your probe lands on a planet with primitive life and starts strip mining it for resources? What if that life was on the verge of developing intelligence? Some proposed safeguards include programming the probes to avoid systems with detected biosignatures or limiting replication to a fixed number of generations. But once you launch something self-replicating into the galaxy, you fundamentally lost control of it. Software can be corrupted by radiation. Instructions can mutate over millions of replications. What starts as a scientific mission could evolve into something entirely different. This brings us back to the question of what we're actually trying to accomplish. Is the goal to have humans physically present in other star systems? Is it to gather scientific data? Is it to ensure some version of humanity survives if Earth becomes uninhabitable? Because those are very different missions with very different solutions. If it's about survival, you don't need humans to travel. You need their DNA. Send a probe carrying frozen embryos and the technology to gestate them. Include enough genetic diversity to establish a viable population. Program AI to raise the first generation with all of human knowledge. The biological humans never experience the journey. They're born at the destination. This removes most of the life support complexity. Frozen embryos don't need food or water or air during transit. They don't suffer radiation damage the way living tissue does. They don't experience the psychological stress of isolation. Store them at cryogenic temperatures, and they can survive indefinitely. The technology required is closer than you might think. We've successfully frozen human embryos since the 1980s. Survival rates after thawing exceed 95%. Artificial womb technology is advancing rapidly. Several research teams have gestated animal embryos to late-stage development in synthetic environments. Scaling that to human application involves ethical hurdles more than technical ones. The AI component is where it gets complicated. You'd need an artificial intelligence sophisticated enough to raise children from infancy to adulthood, teaching them language, social skills, technical knowledge, everything a human parent provides, plus specialized training for survival on an alien world. And you'd need it to do this correctly, because there's no backup plan. No calling Earth for advice when it takes decades for a message to make the round trip. What kind of psychological development happens when your only parent is a machine? How do you instill human values and culture when nobody in the colony has experienced Earth or human society? What happens if the first generation rejects the mission entirely and decides to do something completely different? You could argue that's fine, that the goal is spreading human genetics, not human culture. But genetics alone don't make someone human in any meaningful sense. A colony of people who speak a language they invented, practice customs developed in isolation, and view Earth as a myth their AI parent told them isn't really a continuation of humanity. It's a new species that happens to share our DNA. Unless you include comprehensive cultural programming, digital archives of music, art, literature, history, philosophy, virtual reality experiences of Earth environments, recorded messages from real humans explaining what it means to be part of human civilization. Basically, trying to download culture the way you download software. That raises a different question. How much of human identity is tied to Earth specifically? To walking under a yellow sun in 1G gravity, breathing air with a specific composition, seeing a sky that's blue instead of red or purple or completely alien. If you raise children in a different environment with different sensory inputs, do they develop a fundamentally different consciousness? Studies of sensory deprivation and altered environments suggest the answer is yes. The human brain is incredibly plastic, especially during development. Children raised in radically different conditions develop different neural pathways, different cognitive patterns, different ways of processing reality. They're still human in a biological sense, but their subjective experience of being human might be unrecognizable to us. So you're not really spreading humanity. You're creating something new that evolved from humanity, which might be acceptable depending on your goals, but it's worth being honest about what you're actually doing, and it still doesn't solve the travel time problem. Even with embryos instead of living humans, even with AI instead of human crew, you're still limited by propulsion technology. Chemical rockets aren't getting you to another star in less than tens of thousands of years. Nuclear propulsion drops that to thousands. Fusion might get you into the hundreds. Which brings us to the propulsion technologies that might actually make interstellar travel possible within something resembling a human timescale. Fusion propulsion is the nearest term option that could realistically achieve a significant fraction of light speed. The concept is straightforward. Fuse hydrogen atoms together, release enormous amounts of energy, channel that energy into thrust. It's the same process that powers stars, just controlled and directed. The energy density of fusion is roughly 4 million times greater than chemical combustion. That's not a typo. 4 million. 1 kilogram of fusion fuel contains the energy equivalent of 4 million kilograms of chemical rocket fuel. This changes the entire equation for space travel. Current fusion reactor designs on Earth are massive installations that consume more energy than they produce. But space-based fusion could use a different approach. The direct fusion drive being developed at Princeton Plasma Physics Laboratory is designed to be spacecraft-sized from the start. It uses a magnetic field configuration that's simpler than terrestrial reactors and operates in a regime where plasma instabilities are easier to control. The performance numbers are impressive. A direct fusion drive could accelerate a spacecraft to velocities around 10% light speed. At that velocity, Alpha Centauri is 43 years away. Still a long journey, but within the span of a human career. Launch in your 20s, arrive in your 60s. You'd be old but alive. The technology readiness level is surprisingly high. Static testing of core components is scheduled to begin in 2025. An orbital demonstration mission is planned for 2027. If those tests succeed, a functioning prototype could exist within a decade. But 10% light speed creates new problems. At that velocity, hitting a grain of sand releases energy equivalent to a hand grenade. Interstellar space isn't empty. It contains hydrogen atoms, dust particles, occasional larger debris. Traveling through it at high speed is like flying through a sandstorm, where every grain hits with nuclear-level force. You need shielding. Lots of shielding. Current proposals involve magnetic fields to deflect charged particles and physical armor made of beryllium or other lightweight materials to absorb impacts from neutral atoms. The armor would gradually erode during the journey, ablating away as it protects the spacecraft. You'd need to account for that mass loss in your mission planning. There's also the deceleration problem. Getting up to 10% light speed is one thing. Slowing down when you arrive is another. If you're using fusion rockets, you need to carry enough fuel for both acceleration and deceleration. That roughly doubles your fuel requirements, which increases your initial mass, which requires more fuel to accelerate, which increases mass further. It's the tyranny of the rocket equation at a whole new scale. One proposed solution is the magnetic sail. As you approach your destination, deploy a huge loop of superconducting wire. The star's magnetic field induces current in the wire, creating drag that gradually slows the spacecraft. It's using the destination star's own magnetic field as a brake. This works in theory. Whether it works in practice with a spacecraft moving at 10% light speed is unknown. The forces involved would be enormous. The magnetic sail would need to be kilometers across and somehow survive the stress of deceleration over months or years. Engineering. That is a challenge nobody's solved yet. Alternative approaches skip the deceleration entirely. You don't slow down. You fly through the target system at full speed, gathering as much data as possible during the brief window when planets are in sensor range, then transmit it all back to Earth. It's a flyby mission on an interstellar scale. This is actually more practical than it sounds. Modern sensors can gather tremendous amounts of data in very short timeframes. A spacecraft passing through a star system at 10% light speed would spend hours or days within range of the planets, depending on the system's layout. That's enough time to map surfaces, analyze atmospheric composition, detect magnetic fields, search for biosignatures. The data transmission becomes the bottleneck again. You'd need to store potentially petabytes of information and then transmit it back across light years of distance. The signal strength required is enormous. You're talking about a transmitter that can push data across 4 light years of space, with enough power that Earth-based receivers can detect it above background noise. Current deep space communication systems use massive dish antennas and nuclear power sources to achieve data rates measured in bits per second across interplanetary distances. Scaling that to interstellar distances requires either much larger antennas, much more power, or both. Probably both, or you use a laser. Highly directional, capable of concentrating power into a tight beam, less susceptible to interference than radio. The challenge is keeping the beam pointed precisely at Earth across light years of distance, while your spacecraft is potentially tumbling or maneuvering. Miss by a fraction of a degree, and your signal disappears into empty space. These are solvable engineering problems. Difficult, expensive, requiring technology we haven't built yet, but not impossible, which means fusion-powered flyby missions to nearby stars could happen within this century if we decided to make them a priority. But flyby missions don't establish a human presence. They gather data. For actual colonization, you need to slow down, enter orbit, land. And that requires either carrying enough fuel for deceleration or using some alternative braking method that doesn't consume propellant. This is where things get really speculative, because the next tier of propulsion technology, capable of reaching even higher speeds, involves concepts that sound more like science fiction than engineering. Antimatter represents the theoretical ceiling for chemical propulsion. When matter meets antimatter, they annihilate completely, converting 100% of their mass into energy according to Einstein's equation. No other reaction achieves total conversion. Chemical rockets convert less than 1/1000th of their fuel mass into kinetic energy. Nuclear fission manages about 0.1%. Fusion reaches maybe 0.7%. Antimatter, everything. The energy density is absurd. 1 gram of antimatter reacting with 1 gram of matter releases the energy of a 43 kiloton nuclear weapon. For comparison, the Hiroshima bomb was 15 kilotons. You could theoretically reach Alpha Centauri in just 40 years using antimatter propulsion. That's within a human lifetime. The numbers work perfectly on paper. Here's the problem. We can't make antimatter in useful quantities. CERN's particle accelerators produce maybe 10 nanograms of antiprotons per year at a cost of several $1 million. A nanogram is 1/1000th of a gram. You'd need millions of grams for an interstellar mission. At current production rates, creating enough antimatter for one voyage would take longer than the age of the universe. Even if production became 1,000,000 times more efficient tomorrow, storage presents another nightmare. Antimatter can't touch normal matter, or it instantly annihilates. You need magnetic containment systems that suspend antiprotons in perfect vacuum using electromagnetic fields. Any failure means your fuel explodes, not burns, explodes, with the force of multiple nuclear weapons. NASA studied this extensively in the 2000s. Their conclusion was that antimatter propulsion might be theoretically possible, but practically impossible with any foreseeable technology. The energy requirements for production are too high. The storage is too dangerous. The cost is astronomical. We'd need multiple technological revolutions just to make it remotely feasible. So antimatter joins the list of propulsion systems that work beautifully in physics equations but fail catastrophically when confronted with engineering reality. Which brings us to an uncomfortable truth about interstellar travel. Every propulsion system capable of reaching nearby stars within human timescales requires technology we don't have, can't build, and in some cases violates known physics. Fusion needs controlled reactions we haven't achieved. Antimatter needs production capabilities we can't approach. Light sails need lasers more powerful than anything humanity has constructed. The gap between theory and practice isn't small, it's enormous, unless physics works differently than we think, which leads to the really speculative concepts. Warp drives. The Alcubierre drive, named after physicist Miguel Alcubierre, who described it mathematically in 1994, doesn't move the ship through space. It moves space around the ship. You compress space in front of the vessel and expand it behind, creating a bubble that carries the ship faster than light without technically violating relativity. The ship itself remains stationary within the bubble while space slides past. This works mathematically. The equations balance. Einstein's field equations permit this solution. But there's a catch. Several catches, actually. First, you need exotic matter with negative mass, not antimatter, which has positive mass. Negative mass. Matter that falls upward in gravity fields. Matter that has never been observed and might not exist. The amount required depends on the ship size, but estimates suggest you'd need more negative mass than there is positive mass in the observable universe. Second problem, energy requirements. Even if exotic matter exists, creating and maintaining the warp bubble would require energy equivalent to the mass energy of Jupiter. Some refined calculations suggest maybe you could reduce that to something like the mass of the Voyager probe, but that's still converting an entire spacecraft into pure energy just to power the drive. Third issue, you can't control it from inside. Once the warp bubble forms, you're causally disconnected from the space around you. You can't steer, can't accelerate or decelerate, can't turn it off. You'd need to set your destination before activating the drive and hope nothing gets in the way during the journey. Fourth challenge, you might destroy your destination. Some analyses suggest that when the warp bubble collapses, it releases all the energy it accumulated during the journey as a concentrated burst of radiation that would sterilize everything in front of the ship. Your arrival would be preceded by a wave of destruction. These aren't minor engineering challenges. They're fundamental problems with the concept itself. Alcubierre's original paper was a thought experiment showing that general relativity permits faster than light travel under specific mathematical conditions. It wasn't a blueprint for construction, but assume exotic matter exists and we somehow harness it. Assume we solve the energy problem. Assume we figure out navigation and don't accidentally genocide our destination. You could theoretically reach anywhere in the galaxy in days or weeks of subjective time. The entire Milky Way becomes accessible. That's the promise. The reality is we have no idea if exotic matter exists, no mechanism for creating it if it does, no power source capable of generating the required energy, and no way to control the system even if we built it. Warp drives remain firmly in the realm of mathematical curiosities. Rather than engineering proposals, wormholes face similar problems. General relativity permits shortcuts through space-time. You could theoretically connect two distant points with a tunnel that's much shorter than the normal space between them. Traverse a wormhole and you might cross thousands of light years in seconds. Except wormholes, if they exist naturally, are microscopic and unstable. They collapse almost instantly. Keeping one open requires exotic matter again, that same negative mass substance we can't produce. And creating a wormhole from scratch would require manipulating space-time on scales that make warp drives look simple. Plus, there's the causality problem. Wormholes could potentially allow time travel, creating paradoxes that might make them impossible by fundamental physical law rather than mere engineering limitation. The universe might simply not permit stable traversable wormholes because they'd break causality. So we're back where we started. Every realistic propulsion system is too slow for practical interstellar travel within human lifetimes. Every fast propulsion system requires physics we don't understand or technology we can't build. This is where the human element becomes critical. Because maybe the solution isn't faster ships. Maybe it's longer lifespans, or no lifespans at all. If consciousness can be preserved digitally, uploaded into computers, then biological constraints disappear. A digital mind doesn't age, doesn't need food or water or air, doesn't care if the journey takes 1,000 years. You could launch missions using conventional propulsion and simply wait out the travel time in electronic form. This shifts the problem from physics to neuroscience and computer science. Can consciousness be digitized? We don't know. The human brain contains roughly 86 billion neurons with quadrillions of synaptic connections. Mapping that structure completely is currently impossible. Simulating it in software is beyond our computational capabilities. But assume we eventually figure it out. Upload becomes possible. Now you can travel to other stars using slow, reliable propulsion. Chemical rockets augmented with gravity assists could reach Alpha Centauri in 20,000 years. That's manageable for digital consciousness. Except you face new problems. Digital storage degrades over time. Cosmic radiation can corrupt data. You'd need massive redundancy and error correction to preserve uploaded minds across millennia. The spacecraft would need to repair and maintain itself for longer than human civilization has existed. Any failure means permanent death for the uploaded crew. There's also the philosophical question of whether an upload is really you or just a copy that thinks it's you. If the original biological brain is destroyed during the upload process, are you continuing your existence or creating a duplicate that believes it's continuous? Does the distinction matter? These questions don't have clear answers, but they matter less if the alternative is no interstellar travel at all. Biological approaches exist too. Genetic engineering could extend human lifespans significantly. If you could live 500 years instead of 80, suddenly slow interstellar journeys become viable. You personally might reach another star system. Current aging research suggests lifespan extension is possible in principle. We've already extended maximum lifespan in laboratory animals through genetic modification. Mice engineered with specific genetic changes live 50% longer than normal. Scale that to humans, and you're looking at 120-year lifespans becoming routine. But getting from 120 years to 500 requires more than incremental improvements. You need to fundamentally alter how cells age and repair themselves, prevent telomere shortening, eliminate senescent cell accumulation, repair DNA damage continuously, maintain tissue regeneration indefinitely. We're nowhere near that capability. We don't fully understand the aging process. Multiple mechanisms contribute, and they interact in complex ways. Fixing one might accelerate another. The biological engineering required makes fusion propulsion look straightforward. Then there's hibernation. Not the science fiction version where you freeze and thaw without consequences. real induced torpor similar to what bears do during winter, lower body temperature by 5 to 7 degrees Celsius. Metabolism drops dramatically. Aging slows, though it doesn't stop. NASA's studied this for Mars missions. Reduce crew metabolic needs by 50 to 75% during the long transit. Smaller life support systems, less food and water, lower radiation exposure because cells aren't dividing as rapidly. The spacecraft can be smaller and lighter because the crew spends most of the journey in torpor. Scale this to interstellar missions, and you might extend effective human lifespan enough to reach nearby stars. A 40-year journey at normal metabolism becomes manageable if you're only conscious for a few years of it. The rest passes in dreamless sleep. Challenges exist. Extended torpor in humans hasn't been tested. We don't know the long-term effects on cognition or memory. Bears hibernate for months. We're talking about years or decades. There might be cumulative damage we can't predict. And torpor doesn't stop aging entirely. You still age, just slower. The math still doesn't work for journeys longer than a few decades, which brings us to the most radical solution. Don't send humans. Send the means to create humans. Autonomous spacecraft carrying frozen embryos or even just genetic information. The ship travels for centuries using conventional propulsion. When it arrives, automated systems establish a base, create artificial wombs, grow the first generation. Robots raise them. Uploaded personalities serve as teachers. The colony begins not with travelers, but with people born at the destination. This sidesteps every biological constraint. No need for life support during transit. No aging. No radiation exposure to living tissue. The mission can take as long as needed. 1,000-year journeys become acceptable. But you're creating people who never chose to exist in an alien environment they can't escape. The ethical implications are staggering. Is it right to create conscious beings in such circumstances? Who decides what happens to them? How do you prevent the mission from creating a dystopia? These aren't technical questions, they're moral ones, and they don't have clear answers. Every approach to interstellar travel hits hard limits. Physics limits how fast we can go. Biology limits how long we can survive. Engineering limits what we can build. Economics limits what we're willing to pay for. Ethics limits what we should attempt. Yet the possibility remains tantalizingly real. The stars are unreachably far, but not infinitely so. We've talked about the limitations, the walls closing in from every direction. But here's what actually makes sense, given everything we know right now. Within the solar system, humans can realistically go anywhere. Not quickly, not cheaply, not easily, but it's doable with technology that either exists or is in active development. Mars is the obvious first target. 9 months using current chemical propulsion. 3 months if we push Starship to its limits with multiple refueling runs. Eventually down to 45 days with nuclear thermal propulsion once someone actually builds and tests a flight-ready reactor. The round trip still takes years because of orbital mechanics. You can't just turn around and come home. You wait for the planets to align again. But it's within human tolerance. Uncomfortable, dangerous, but survivable. The asteroid belt opens up with better propulsion. Nuclear electric drives make efficient long-duration burns possible. You could visit Ceres, mine resources, establish outposts. Travel times measure in months to a few years, depending on your target and how much delta V you can generate, still well within a human lifetime. Still using technology we understand even if we haven't perfected it yet. Jupiter's moons get interesting. Europa, Ganymede, Callisto, potential subsurface oceans, possible biosignatures. With fusion propulsion, you could reach Jupiter in under 2 years, explore the moon system, return within a decade total. That's ambitious, but not absurd. Saturn takes longer, 5 to 7 years one way, even with advanced propulsion, but still achievable. A career-spanning mission, rather than a suicide run. The outer solar system becomes accessible with fusion drives and life extension technology. Uranus and Neptune sit at the edge of feasibility. 10 to 15-year transit times each way. You'd need crew rotation, hibernation, or significant lifespan increases. Probably all three. But someone born today might live to see humans orbit Neptune. That's not fantasy. That's engineering and biology we're actively working on. Beyond Neptune, you hit the real boundary. Not a physical wall, but a practical one. The Kuiper belt extends to about 50 astronomical units. Pluto's out there at 40 astronomical units on average. The New Horizons probe took 9 years to reach it. With fusion propulsion, you might cut that to 4 or 5. Still manageable. But past 50 astronomical units, you're entering the scattered disk. Objects spread across hundreds of astronomical units. Travel times balloon. Even fusion drives struggle. The Oort cloud represents the edge of the Sun's gravitational dominance. It starts around 2,000 astronomical units and extends to maybe 100,000 astronomical units. That's nearly 2 light years. At fusion drive speeds, reaching even the inner Oort cloud takes centuries. The outer edge, thousands of years. You're not sending humans there with any technology we can currently envision. Maybe probes, maybe robotic explorers, but not people. So the realistic boundary for human exploration in one lifetime is somewhere between 50 and 100 astronomical units, the outer planets and inner Kuiper belt. That's your sphere of possibility using advanced but theoretically achievable technology. Fusion propulsion, radiation shielding, closed-loop life support, moderate life extension, possibly hibernation. All of it requires massive investment and decades of development. But nothing violates physics. Nothing requires breakthroughs we have no path toward. What about speed records? How fast could we actually push a human-carrying spacecraft? The Parker Solar Probe hit 430,000 miles per hour. That's 0.064% the speed of light. Impressive for an unmanned probe using gravity assists. But putting humans on that trajectory means adding massive life support systems, radiation shielding, provisions. The spacecraft becomes exponentially heavier. You lose most of your speed advantage. Chemical rockets max out around 40,000 miles per hour in practical terms. That's what Apollo achieved. Modern systems aren't dramatically faster. Nuclear thermal propulsion doubles exhaust velocity. You might hit 80,000 to 100,000 miles per hour with an optimized trajectory. Still nowhere near Parker Solar Probe speeds. Nuclear electric propulsion trades thrust for efficiency. You accelerate slowly but continuously. Over months, you could potentially reach similar velocities to Parker, maybe slightly higher, but you're still talking about fractions of a percent of light speed. Fusion changes the equation. Direct fusion drive concepts suggest continuous acceleration at meaningful fractions of a g. Maintain that for weeks, and you're approaching 1% light speed. That's fast enough to cross the solar system in months rather than years, fast enough to make the outer planets accessible. But 1% of light speed is still glacial for interstellar distances. Proxima Centauri is 4.24 light-years away. At 1% light speed, you arrive in 424 years, multiple generations, not a single lifetime. To reach nearby stars within one human lifetime, you need 10% to 20% of light speed minimum. That requires energy densities chemical and fission fuels can't provide. Fusion gets you partway there, but the engineering challenges multiply. Containing plasma hot enough to fuse while channeling that energy into thrust. Shielding the crew from radiation. Managing heat that would vaporize any known material. We're decades from solving those problems, even in theory. Antimatter propulsion could theoretically push you to 40% light speed. At that velocity, Proxima Centauri is a decade away. Time dilation starts becoming significant. Your subjective journey time drops below 10 years. But producing antimatter in useful quantities requires energy inputs we can't currently generate. CERN makes nanograms per year at costs measured in millions of dollars per nanogram. Scaling to the grams or kilograms needed for propulsion would require energy production exceeding total global output. We're not talking about difficult, we're talking about impossible with current infrastructure. Takes decades in Earth's reference frame. Might feel like years to you. At 99% light speed, the compression becomes extreme. You could theoretically cross the galaxy in a human lifetime from your perspective. The catch is acceleration. Reaching 99% light speed requires energy equal to many times your spacecraft's rest mass. E equals mc squared isn't just a formula, it's a fundamental barrier. Your fuel requirements approach infinity as you near light speed. The only theoretical workaround is perfect matter-antimatter annihilation. 100% conversion of mass to energy. Even then, you hit diminishing returns. The faster you go, the more massive you become from Earth's reference frame, requiring exponentially more energy to accelerate further. You could burn your entire spacecraft as fuel and still not reach light speed. So realistically, with technology, we can currently imagine building human crewed missions max out around 5% to 10% light speed. That's fusion-powered spacecraft with decades of continuous acceleration. At 10% light speed, Proxima Centauri is 42 years away, an entire human lifetime. You'd leave Earth as a young adult and arrive in your 60s. Assuming you survive the journey, assuming the technology works perfectly, assuming nothing breaks in 4 decades of continuous operation. That's your actual boundary. The inner solar system is easy. The outer solar system is challenging but doable. Nearby interstellar space requires technology we're actively developing. Anything beyond 5 light years demands either generation ships, radical life extension, or physics we don't yet understand. And that assumes you're just trying to get there. slowing down to actually explore or colonize requires just as much energy as speeding up. Unless you're planning a flyby, you need enough fuel to decelerate. That doubles your energy requirements. It halves your maximum range. A spacecraft that could theoretically reach 10% light speed with its full fuel load might only manage 5% if it needs to stop at the destination. The numbers get worse when you account for return trips. Unless you're establishing a one-way colony, you need fuel to come home. That triples or quadruples your initial mass, which means more fuel to accelerate that mass, which means even more fuel. The rocket equation bites you hard. Every kilogram of payload requires exponentially more fuel. This is why generation ships and seed ships keep appearing in serious discussions. Not because they're good solutions, because they might be the only solutions that work with physics as we understand it. You accept that the journey takes centuries. You design around that constraint rather than fighting it. But generation ships introduce problems that make technical challenges look simple. How do you maintain social cohesion across multiple generations? What happens when the fifth generation decides they don't want to complete the mission? How do you preserve knowledge and skills over centuries? What if crucial technology breaks and nobody remembers how to fix it? Project Hyperion studied these questions. Their baseline design assumed 1,000 people minimum, enough genetic diversity to prevent inbreeding, enough social diversity to maintain culture, large enough that losing a few people doesn't doom the mission, small enough to be theoretically manageable. The spacecraft would be massive, several kilometers long, rotating sections for artificial gravity, agricultural zones for food production, manufacturing capability for repairs. Essentially, a small city in space. This is for a journey to Proxima Centauri. This is for a journey to Proxima Centauri. 4 light years away, the closest star. Anything farther multiplies every problem, which loops back to the fundamental question: how far can humans realistically travel in one lifetime? The answer depends entirely on what you mean by realistic. If you mean with current technology, Mars is about it. Maybe Jupiter's moons if you're willing to spend your entire career on one mission. If you mean with technology we're actively developing, the outer solar system becomes accessible. Saturn, Uranus, Neptune, the Kuiper Belt, 50 to 100 astronomical units from the Sun. If you mean with technology that doesn't violate known physics but requires major breakthroughs, nearby interstellar space opens up. Proxima Centauri might be reachable in a single lifetime. Barnard's star at 6 light-years becomes possible. Sirius at 8.6 light-years pushes the limits. Beyond that, you're into speculation. Warp drives, wormholes, physics we don't understand. Maybe possible, maybe not. But not something you can plan a mission around. The honest answer is probably disappointing. Humans born today will likely see Mars colonized, possibly bases on Jupiter's moons, maybe the first fusion-powered spacecraft reaching Saturn or Uranus. But interstellar travel, that's for future generations, unless we discover something fundamental about physics that we're currently missing. The universe is vast. The distances are brutal. The speed of light is both incredibly fast and frustratingly slow. Fast enough that light crosses the solar system in hours. Slow enough that it takes years to reach even the nearest stars. And we can't even approach light speed, let alone exceed it. So you're left with a choice. Accept the limitations and focus on what's achievable. Or keep pushing, hoping that breakthrough comes, that someone figures out fusion propulsion, that life extension becomes reality, that the pieces fall into place, allowing that one lifetime journey to another star. It's not impossible, just improbable. And the difference between those two words contains all of human history. But here's where things get interesting. That improbable breakthrough might be closer than you think. Not because we've discovered warp drives or cracked exotic physics, because we're starting to understand that the question itself is backwards. We've been asking, how do we go faster? When we should be asking, how do we make time work for us? Relativistic time dilation, Einstein's gift to future astronauts. At everyday speeds, time moves the same for everyone. You drive to work, your friend stays home, you both age identically, but approach light speed and reality fractures. Time becomes personal, subjective, flexible. Travel at 95% light speed, and something remarkable happens. For every 10 years on your ship's clock, 32 years pass on Earth. You don't feel different. Your heartbeat stays normal. Your thoughts move at regular pace. But the universe outside is aging faster. Difference is microseconds, but it's real. The difference is microseconds, but it's real. Scale that up to near light speed, and the effect becomes dramatic, which means the answer to how far can we travel in a lifetime becomes anywhere, if we're willing to pay the price. The price being everyone you know aging faster than you. Imagine leaving Earth at age 30. Destination: a star system 40 light years away. Your ship accelerates constantly at 1G. Comfortable artificial gravity pushing you toward the floor. After a year of subjective time, you're moving at a significant fraction of light speed. After 5 years, you're deep into relativistic territory. Time dilation kicks in hard. You arrive at your destination having aged 20 years. You're 50 now. The journey felt real, long, sometimes boring. But back on Earth, 45 years have passed. Friends are elderly or dead. Technology has transformed. The world you left is history. But you made it. 40 light years in one lifetime. Keep accelerating and the numbers get wilder. A ship maintaining constant 1G acceleration could theoretically reach the Andromeda Galaxy in 28 years ship time. The travelers would experience less than 3 decades. Earth would age 2.5 million years. You could cross the observable universe in a human lifetime. From your perspective, this is where the physics gets simultaneously beautiful and cruel. Time dilation doesn't just make distant destinations reachable. It makes them one-way trips through time. Leave Earth today, and you're not just traveling through space. You're traveling into Earth's future. Every light year you cover at high speed puts you decades or centuries ahead of everyone who stayed behind. There's no going home. Not to the home you left. So the engineering question becomes, can we actually build ships that accelerate continuously? Because chemical rockets burn for minutes, not years. Ion drives run for months, but provide minuscule thrust. Nuclear thermal doubles performance, but still can't sustain acceleration indefinitely. Fusion changes the equation entirely. A fusion drive could theoretically maintain thrust for years, decades even. The fuel is hydrogen isotopes, abundant in space. The exhaust velocity is measured in percentages of light speed rather than kilometers per second. The energy density is millions of times higher than chemical reactions. Princeton's direct fusion drive concept could reach Pluto in 4 years. That's with current designs. Not optimized for maximum performance. Scale it up, improve the efficiency, add better magnetic confinement. You're looking at sustained acceleration approaching 1G, which opens the door to relativistic travel without requiring antimatter or exotic physics. But fusion is hard. We've been working on it for 70 years. Every decade brings promises of just 20 more years. Recently, though, the timeline shortened. Multiple private companies achieved fusion ignition. Different approaches, different designs, all showing that fusion isn't impossible, just difficult. ITER in France will demonstrate sustained fusion by the 2030s. Smaller reactors are testing alternative confinement methods. Some use lasers, others magnetic fields. A few try unconventional geometries. At least one will work for propulsion. The question isn't if anymore, it's when. Meanwhile, other technologies are advancing in parallel. Life extension research is making real progress. Senolytics clear damaged cells. Gene therapy extends healthy lifespan in animals. Caloric restriction mimetics provide benefits without starvation. Aging isn't inevitable anymore. It's a solvable problem. Combine extended lifespan with relativistic travel, and the range explodes. Live to 150 years old. Spend 50 traveling at 90% light speed. You've personally experienced 50 years. Earth has aged 115 years. You've covered over 100 light years subjectively. Your biological age is 80. That encompasses thousands of star systems, millions of potentially habitable worlds, and we haven't touched on hibernation yet. Not cryonic freezing. That's still science fiction. But torpor, induced hibernation that reduces metabolic rate by cooling the body 5 to 7 degrees Celsius. SpaceWorks Enterprises proved the concept for NASA. 2 weeks in torpor. Wake up. Rest briefly. Back under. Astronauts in torpor don't experience time. They're not conscious, not aging normally, not consuming resources. A journey that feels like 50 years might subjectively feel like 5. Maybe less if the technology improves. Stack these advances, and you're looking at practical interstellar exploration. A 100-year-old astronaut with life extension treatments. 40 years in hibernation. Traveling at 90% light speed. They experience maybe 10 years subjectively. They've covered 80 light years. They're biologically 110. Still healthy. That's not science fiction. That's combining technologies we're actively developing. The real barrier isn't physics, it's willingness. Who volunteers for a mission where everyone they know will be dead when they arrive? Where Earth's entire civilization might have transformed beyond recognition? Where you can never go back? Turns out quite a few people would. Studies show roughly 30% of surveyed individuals would accept a one-way mission to Mars. For interstellar travel with time dilation, the percentage drops but doesn't disappear. Some people crave exploration more than connection. Some see themselves as pioneers rather than citizens. History shows this pattern repeatedly. People crossed oceans knowing they'd never return, sailed into unknown waters, climbed impossible mountains, humans consistently choose adventure over safety when given the option. An interstellar mission would attract volunteers, not billions, but enough, especially if the destination offers something Earth doesn't. A pristine world, unlimited resources, escape from overcrowding or political instability, freedom to build new societies with different rules. The first interstellar missions won't be exploration, they'll be colonization. Because there's no point sending people to look around and come back. Time dilation makes that impossible. You send people to stay, to build, to establish humanity's presence beyond the solar system. Which brings up the economics. Why spend trillions on interstellar missions when you could invest in Earth? The answer is redundancy, survival, insurance. Earth faces existential risks, asteroid impacts, supervolcano eruptions, nuclear war, engineered pandemics, climate catastrophe. I gone wrong. Any of these could end civilization or humanity entirely. One planet means one point of failure. Spreading to Mars reduces risk, but not enough. Mars is close. Whatever destroys Earth might reach Mars. Solar flare, gamma ray burst, rogue AI with patience. True redundancy requires interstellar distance. Colonies separated by light years can't be wiped out simultaneously. They're isolated, protected by sheer distance. From that perspective, interstellar colonization isn't optional. It's mandatory for long-term survival. The timeline gets interesting when you consider economic incentives. Mining asteroids could be profitable within decades. Helium-3 from the Moon might fuel fusion reactors. Mars colonization could be self-sustaining by 2010. Each step makes the next easier, cheaper, more practical. Asteroid mining develops heavy lift capabilities. Lunar industry proves closed-loop life support. Mars colonies perfect long-duration spaceflight. All of these feed into interstellar missions. By 2015, launching an interstellar probe might cost what launching a Mars mission costs today. Not cheap, but achievable. Within the budget of nations or corporations. By 2020, crewed interstellar missions might be economically viable. Not routine, but possible without bankrupting civilization. That's assuming steady progress, no major setbacks, no civilizational collapse. Big assumptions. But even with setbacks, the trajectory points outward. Humans have been expanding since we left Africa. We crossed continents, oceans, now space. The pattern holds. So here's the timeline that emerges from current technology and reasonable extrapolation. 2030s, fusion propulsion prototypes, life extension treatments, advanced hibernation, all proven but not integrated. 2050s, first fusion-powered spacecraft, Mars colonization underway, humans living in space long-term. 2070s, outer solar system accessible within single careers, Neptune within 15 years travel time, Kuiper Belt settlements, 21st century, first interstellar probes launched, unmanned, reaching Alpha Centauri in 50 to 70 years, reporting back. 21st century, first crewed interstellar mission departs, destination Proxima Centauri, travel time 30 years subjective, crew in hibernation most of the journey, Earth ages 60 years. They arrive, establish colony, never return. 22s, multiple interstellar colonies. communication via laser takes years. Each develops independently. Humanity becomes multi-stellar species. That's the optimistic timeline, the one where technology advances smoothly and nothing catastrophic happens. The pessimistic timeline adds decades or centuries to each step. Maybe fusion proves harder than expected. Maybe life extension stalls. Maybe economic collapse delays everything. But the destination remains the same. Eventually, humans travel to other stars. The question is when, not if, because the alternative is staying confined to one solar system. One planet really, since other worlds in our system are marginal. That's not sustainable long term. Either we expand or we stagnate, eventually decline, possibly go extinct. Expansion is survival. Interstellar travel is inevitable. Your lifetime specifically? That depends on your age. If you're 20 now, you'll probably see fusion spacecraft and Mars colonies, maybe early interstellar probes. If you're younger, add crewed interstellar missions to that list. If you benefit from life extension, you might live to see humanity spreading across multiple star systems, not traveling there yourself necessarily, but watching it happen. Knowing humans walk on worlds circling other suns, that's the real answer to how far humans can travel in one lifetime. Individually, maybe Mars, maybe the outer solar system if you're lucky, and technology advances quickly. Collectively as a species, potentially dozens of light years within the next 2 centuries. The universe is vast. The distances are brutal. But they're not impossible. They just require accepting that one lifetime means different things depending on your velocity. That going far means leaving home permanently. That exploration and sacrifice are inseparable. Some will make that choice, will volunteer for journeys they can't return from, will accept aging slower than everyone they've ever known. And when they do, they'll carry humanity to stars we currently see only as points of light. That's the real answer to how far humans can travel in one lifetime. Individually, maybe Mars, maybe the outer solar system if you're lucky, and technology advances quickly. Collectively as a species, potentially dozens of light years within the next 2 centuries. The universe is vast, the distances are brutal, but they're not impossible. They just require accepting that one lifetime means different things depending on your velocity. That going far means leaving home permanently. That exploration and sacrifice are inseparable. Some will make that choice, will volunteer for journeys they can't return from, will accept aging slower than everyone they've ever known. And when they do, they'll carry humanity to stars we currently see only as points of light. The people who make that journey won't be like us. Not psychologically. You can't send someone who needs quarterly performance reviews to Proxima Centauri. Can't send someone who gets homesick after a week abroad. The selection criteria for interstellar crews will prioritize traits we don't typically value. Comfort with isolation, indifference to status, ability to find purpose in tasks that won't be completed for decades. Current astronaut selection focuses on intelligence, physical health, teamwork, important for 6-month ISS missions, inadequate for 30-year voyages. Future criteria might include low attachment to specific places, high tolerance for delayed gratification, capacity to form deep bonds, with small groups, psychological profiles that would seem odd on Earth but thrive in isolation. These aren't qualities you advertise for. They're things you discover through observation, through watching how people respond to long-term isolation studies, through monitoring who volunteers for Antarctic winter stations and actually enjoys it, through identifying individuals who genuinely prefer solitude to crowds. They exist, not many, but enough. The ships themselves will be unlike anything currently flying. Chemical rockets won't cut it. Too slow, too inefficient. Nuclear thermal propulsion gets you to Mars in 3 months instead of 9. Useful, but still inadequate for interstellar distances. You need fusion at minimum, preferably antimatter, technologies that currently exist only in theory or extremely limited laboratory demonstrations. Fusion propulsion is close. Multiple approaches show promise. Magnetic confinement, inertial confinement, direct fusion drives, all face engineering challenges. None violate physics. The direct fusion drive being developed could reach Pluto in 4 years. Compare that to New Horizons, taking 9 years. That's the kind of improvement that changes what's possible. Scale that up. More power, larger spacecraft, continuous acceleration for months instead of weeks. Suddenly, Neptune is reachable in 5 years, the Kuiper Belt in 8, Oort cloud in 20. Still not interstellar, but approaching the threshold where interstellar becomes conceivable rather than absurd. Antimatter changes everything. Theoretically, energy density 9 times 10 to the 16th joules per kilogram. Nothing comes close. Matter-antimatter annihilation is perfectly efficient. All mass converts to energy. No waste. No theoretical limit except light speed itself. Beam core antimatter rockets could reach 40% light speed. Alpha Centauri in 11 years. Barnard Star in 15. Sirius in 22. Problem is production. CERN's antiproton decelerator produces 10 nanograms of antiprotons annually. Cost, several $1 million. Producing 1 gram would require 25 million kilowatt hours. Current energy costs make that prohibitively expensive. Doesn't mean impossible. Just means we need better production methods. Future antimatter factories might use solar power. Build them near the sun where energy is abundant. Use magnetic containment to store antimatter long-term. Accumulate enough for missions over years or decades. Expensive initially, but costs decline with scale. First antimatter gram costs billions. 1,000th gram costs millions. Millionth costs thousands. Economics of scale apply even to exotic technologies. Time dilation becomes relevant at these speeds. Traveling at 40% light speed produces noticeable effects. Ship time runs slower than Earth time, not dramatically, but measurably. Journey to Alpha Centauri takes 11 years Earth time. Might feel like 9 years to the crew. Small difference, but it compounds. At higher speeds, the effect intensifies. 90% light speed, time dilation factor is 2.3. 10 years shipboard equals 23 years Earth time. 95%, factor increases to 3.2. 10 years becomes 32. 99%, factor jumps to 7. Your decade-long journey ages. Earth 70 years. This creates strange scenarios. You depart for Alpha Centauri at 95% light speed. Journey takes 4.5 years from your perspective, but Earth experiences 14 years. You return. Earth has aged 28 years. Your younger sibling is now older than you. Your children are your age. Your grandchildren are older than your children were when you left. Most people find this disturbing, understandably, but some won't. Some will see it as liberation, freedom from Earth's timeline, ability to witness future eras. These are the people who crew interstellar missions, not despite the time dilation. Because of it, radiation remains the persistent challenge. Galactic cosmic rays, solar particle events, both dangerous, both unavoidable in deep space. Earth's magnetosphere protects us. Mars lacks meaningful protection. Interstellar space has none whatsoever. Crew traveling to Proxima Centauri face decades of exposure. Current shielding is inadequate. Water helps. Hydrogen-rich materials absorb radiation effectively. Surround crew quarters with water tanks. Use wastewater, drinking water, anything liquid. Provide some protection, not complete, not enough for multi-decade voyages. You need active shielding, magnetic fields that deflect charged particles, plasma shields that absorb radiation. Technologies currently theoretical, but physically plausible. Alternatively, accept the risk, calculate acceptable exposure limits, select crew members who've already had children, who don't plan more, who accept increased cancer risk as mission cost. Sounds grim, but climbing Everest kills 3% of climbers. People still volunteer. Interstellar missions might have similar risk profiles. Some will accept those odds. Hibernation technology helps. Torpor reduces metabolic rate. Body temperature drops 5 to 7 degrees Celsius. Metabolism slows dramatically. Crew sleeps weeks or months at a time, wakes periodically, then returns to torpor. Journey to Mars becomes subjective weeks instead of months. Journey to outer planets becomes subjective months instead of years. NASA is actively developing this. Torpor-inducing transfer habitat, therapeutic hypothermia adapted for spaceflight. Current protocols allow 2 weeks continuous torpor. Future versions might extend that to months. Stacked torpor periods could cover most of a multi-year journey. Crew experiences only the wake periods. Subjective journey time drops by 60 to 80%. Benefits extend beyond time perception. Hibernating crew needs less food, less water, less oxygen, smaller living quarters, lower mass requirements, cheaper launches, faster transit times, fewer psychological issues from isolation. Bears hibernate 6 months annually without muscle loss. Understanding that mechanism could prevent spaceflight muscle atrophy. Generation ships represent the alternative approach, except that journeys take centuries. Design accordingly. Build ships large enough for communities. 1,000 people minimum. Closed-loop ecosystems. Self-sustaining food production. Complete recycling of water and air. Ship becomes traveling civilization. Project Hyperion explored this concept. Detailed engineering studies. Quarter-millennium journey duration. Population of 1,000 plus or minus 500. Destination planet prepared by precursor probe. Artificial ecosystem established before arrival. Ship maintains stable environment across 10 to 15 generations. Challenges are immense, technical and social. Life support must function flawlessly for 250 years. No resupply, no repair missions, complete self-sufficiency. Any critical failure means extinction. Maintenance knowledge must transfer across generations. Can't afford to lose expertise. Social challenges might be worse. How do you maintain purpose across generations? Initial crew volunteered, chose the mission. Their children didn't. Born aboard ship, never asked to spend lives traveling to destination they'll never see. How do you prevent resentment? Rebellion? How do you preserve cohesion when no one remembers Earth? Some proposals suggest genetic engineering, modify crew psychology, increase satisfaction with confined environments, reduce novelty seeking, enhance cooperation. Sounds dystopian, might be necessary. Alternative is risking mission failure due to social collapse. Which is worse, modifying crew psychology or watching 1,000 people die in space because their grandchildren gave up? No easy answers, but someone will attempt it. We'll build generation ships and launch them toward distant stars. We'll gamble that human adaptability extends to multi-generational voyages. History suggests they might succeed. Humans have survived worse, adapted to harsher environments, crossed greater relative distances with less technology. Polynesian voyagers crossed Pacific Ocean in outrigger canoes. No navigation instruments, no charts, just observation and courage. Journeys took months. Many died. Some succeeded. Populated islands across vast ocean. Generation ships are similar. Longer duration, higher technology, same fundamental gamble. The first interstellar missions won't be exploration. They'll be colonization. One-way trips. Crews departing knowing they'll never return. Either they succeed in establishing colony or they die trying. No middle ground. No rescue possible across light years. Complete self-reliance from departure until success or extinction. This changes mission psychology. Explorers expect to return, report findings, receive recognition. Colonists expect nothing. They go to build something permanent, something that outlasts them. Different motivation entirely, requires different personality type. Less ego, more dedication to abstract future. These missions will carry human diversity, genetic and cultural. Can't afford bottlenecks, need broad gene pool, multiple cultural traditions, different knowledge systems, maximum adaptability for unknown conditions. Crews will be deliberately heterogeneous, selected for diversity rather than similarity. Communication lag creates effective independence. Message to Alpha Centauri takes 4.3 years. Response takes another 4.3 years. Minimum 8-year conversation cycle. Real-time dialogue impossible. Colony can't ask Earth for help with urgent problems. Must solve everything locally. Earth can send advice. Colony might implement it, or might have already solved problem differently by the time message arrives. Over decades, this creates divergence. Colonies develop independently, adapt to local conditions, evolve distinct cultures, eventually become separate civilizations, still human, but not Earth human. Something new, something shaped by different environment and different constraints. This is how humanity becomes multistellar species. Not through maintaining connection, through accepting separation, through launching colonies that will inevitably become independent, through recognizing that expansion means diversification, that unity across light years is impossible, that the future of humanity is many humanities. Your lifetime sits at the beginning of this process. Current spacecraft barely reach outer solar system. Voyager 1 has traveled for nearly 50 years and is only 25.7 billion kilometers away. Sounds far. It's barely started. At current speed, Voyager travels 1 light year in 19,000 years. Proxima Centauri would take 80,000 years, but Parker's solar probe reached 430,000 miles per hour, nearly twice Voyager's speed. Not much in cosmic terms, but progress. Each generation builds on previous achievements. Voyager represented 1970s technology. Parker represents 2010s. What will 2040s achieve? 2070s? 2000s? Fusion propulsion might launch in 2030s. Mars colonies might establish in 2040s. Outer system settlements might appear in 2060s. First interstellar probes might depart in 2080s. First crewed missions might launch in 2010s. Each step enables the next. Each achievement makes impossible possible. So how far can humans travel in your lifetime? Depends entirely on when you're reading this and how long you live. Someone born in 2000 might see Mars colonies and fusion spacecraft. Born in 2020, add interstellar probes. Born in 2040, potentially witness first crewed interstellar departure. Life extension changes calculations. If you live to 150, you see much more. If you reach 200, you might witness humanity spreading across multiple star systems, not traveling there yourself, but watching it happen. Seeing humans walk on worlds we currently observe only through telescopes. The real limit isn't technology, it's commitment. Every breakthrough requires investment. Every mission requires volunteers. Every colony requires people willing to leave everything behind. Technology will advance. Physics allows it. Economics will eventually support it. Question is whether enough humans will choose to go. History suggests yes. Every frontier attracted volunteers. Every dangerous journey found crew. Every colony found settlers. Interstellar missions will be no different. Harder, more dangerous, more permanent. But some will go. Will volunteer for journeys they can't return from. Will accept aging slower than everyone they know. Will carry humanity to distant stars. And when they arrive, when they look up at unfamiliar constellations and see Sol as just another star, they'll know they traveled as far as humans can go. Not in distance. Distance is arbitrary, but in commitment, in sacrifice, in willingness to become something new. That's the real measure of how far we can travel. Not light years, not parsecs, but how far we're willing to go from everything familiar, how much we're willing to change to reach new worlds, how much we're willing to sacrifice to ensure humanity doesn't end on one planet orbiting one star. The distances are vast, the challenges are real, the odds are uncertain, but the journey has already begun. Every spacecraft launched, every technology developed, every volunteer selected, all steps toward the same destination, toward humanity scattered across the stars, toward a future where one lifetime can span solar systems, where going far enough means never coming back, where exploration and permanence are inseparable. The answer to how far you can travel in one lifetime keeps changing, not because physics changes, because one lifetime is becoming a variable instead of a constant. Right now, today, with technology that exists, you could theoretically reach Mars. 9 months there, 16 months waiting for orbital alignment, 9 months back. That's 34 months total. Almost 3 years. Doable. Uncomfortable. Radiation exposure near NASA's career limits. Bone density loss. Muscle atrophy. But survivable. Push that to 90-day transits using Starship with orbital refueling, and suddenly Mars becomes accessible. Multiple trips possible in one career. The round trip drops to maybe 2 years total, including surface time. That's within human tolerance. Barely. But within it, nuclear thermal propulsion cuts Mars to 45 days. The outer planets become reachable. Jupiter in under 2 years. Saturn in 3. Neptune in maybe 15 years round trip. Still most of a career. But one person could visit Neptune and return before retirement. Fusion changes everything. Direct fusion drive concepts suggest Pluto in 4 years. The Kuiper Belt becomes accessible within a decade. You could explore the outer solar system and come back with years of life remaining. Not comfortable, not safe by Earth standards, but possible. That's the near-term answer. The technology we're actively developing. The missions that might happen in the next 50 years. Real engineering, real physics, real timelines. Beyond that, you hit the barrier. The one where conventional thinking fails. Where you need something radical. Either propulsion that doesn't exist yet, or acceptance that the journey takes longer than traditional lifespans allow. This is where the timeline splits into multiple futures. Path 1. Generation ships. Accept that reaching other stars takes centuries. Build vessels large enough for complete ecosystems. Launch them knowing everyone aboard will die before arrival. Their children will die. Their grandchildren will die. Somewhere 5 to 10 generations later, their descendants arrive at a world none of the original crew will ever see. Project Hyperion designed ships for exactly this. 1,000 people minimum. Quarter millennium journey. Closed-loop life support. Complete self-sufficiency. Social structures that maintain cohesion across timescales. Longer than most nations have existed. It's technically possible. Socially uncertain. Ethically complicated, but possible. Path 2. Hibernation. Reduce the subjective journey time. Sleep through the boring parts. Wake up at the destination. Current torpor research suggests weeks are achievable. Future developments might extend that to months or years. Stack enough hibernation cycles and a 40-year journey feels like 5. You age slower, experience less, arrive having missed decades, but having lived only years. Combine this with moderate life extension and suddenly, century-long journeys become survivable. You're 150 years old biologically, but you've only been conscious for 80 of those years. The rest passed in dreamless hibernation while your ship crossed the void. Path 3. Accept time dilation. Build ships that reach significant fractions of light speed. At 90% light speed, time aboard runs at 1/3 Earth's rate, a journey that takes 30 years from Earth's perspective feels like 10 to you. You leave everyone behind. Everyone you know ages faster than you. Your children become older than you. Your grandchildren might be elderly when you return, but you traveled farther than anyone thought possible. Covered distances that should take lifetimes in what felt like years. The price is permanent separation from everyone you knew. The reward is reaching destinations that were supposed to be impossible. This path requires antimatter propulsion, or something equally exotic. technology that exists only in theory, but theory based on proven physics, not speculation, not fantasy, just engineering we haven't achieved yet. Path 4. Redefine the journey entirely. Don't send humans, send the means to create them. Frozen embryos in autonomous spacecraft, artificial wombs that gestate them on arrival, AI systems that raise the first generation. The people who walk on new worlds never experience the journey. They were born at the destination, created specifically for that environment. This solves every biological constraint. No life support during transit, no aging, no radiation exposure to living tissue. The mission can take as long as needed. 1,000-year journeys become acceptable because nobody experiences them, but you're creating people who never chose their existence, who are engineered for a specific purpose on a specific world. The ethics are complicated. The necessity might override objections. Each path is possible. Each requires different technology, different timescales, different sacrifices. None are easy. None are certain. All remain within known physics. The real question isn't which path we'll take. It's how many we'll take simultaneously. Some missions will use generation ships. Slow, reliable, proven technology. High social risk, but low technical risk. Others will attempt hibernation. Faster, riskier, dependent on biological systems functioning perfectly for decades. A few might push for relativistic speeds. Antimatter drives if we solve production. Time dilation as a feature rather than a bug. And some will send embryos, will create new humans on distant worlds, will establish colonies that never knew Earth except as history, transmitted across light years. All of this is happening, not in distant hypothetical futures. Now, fusion propulsion tests are scheduled. Life extension research is advancing. Hibernation protocols are being developed. Embryo preservation is proven technology. The pieces exist. They just haven't been assembled yet. Your lifetime specifically sits at the transition point, the moment when interstellar travel shifts from science fiction to engineering challenge. When the question stops being, can we, and starts being, when do we? If you're reading this in 2024, you might see Mars colonies, probably fusion spacecraft, possibly the first interstellar probes departing. If you benefit from life extension treatments that are currently in development, add crewed interstellar missions to that list. If you're young enough and lucky enough, you might witness humanity becoming a multi-stellar species, not traveling there yourself. That's still unlikely. But watching it happen, seeing humans walk on worlds circling other suns, receiving data from colonies light years away, watching new civilizations emerge in real time with 4-year communication delays. The universe is vast. The distances are brutal. The speed of light is both incredibly fast and frustratingly slow. We can't exceed it, might never exceed it. Physics might make that genuinely impossible, but we can approach it, can reach significant fractions of it, can use time dilation to make vast distances survivable, can build ships that function for centuries, can modify ourselves to endure longer journeys, can create new humans at distant destinations. The barriers aren't physics. They're engineering, economics, and will. We know how to do most of this in theory. We just haven't built it yet, haven't committed the resources, haven't decided it's worth the cost. That calculation changes when Earth faces existential risk, when one planet feels too fragile, when the survival instinct that drove us out of Africa drives us out of the solar system, when staying means eventually dying and leaving means possibly surviving, to stars that are currently just points of light, to stars that are currently just points of light. And when they arrive, whether it takes decades or centuries, whether they're the original crew or their descendants or artificially created colonists, they'll look up at alien skies and see Sol as just another star. They'll know they traveled as far as humans can go in one lifetime. Not necessarily one human lifetime, but in the continuous lifetime of the species. The unbroken chain from Africa to Alpha Centauri, that's the real answer. How far can we travel? As far as we're willing to go. As far as physics allows. As far as determination carries us. The specific number in light years matters less than the commitment to keep expanding, to keep exploring, to refuse to accept one planet as humanity's permanent limit. Mars is within reach. The outer solar system is accessible with near-term technology. Nearby stars become possible with fusion propulsion and time dilation. Distant stars require generation ships or radical life extension or technologies we're still developing. The observable universe remains theoretical, but not impossible, just improbable given current knowledge. Every answer depends on assumptions. What technology develops, what resources we commit, what sacrifices we accept. Change the assumptions and the distances change, but the trajectory remains consistent, outward, always outward, farther with each generation. You probably won't travel to other stars yourself, unless you're very young and very lucky, and life extension advances faster than expected. But you'll see the foundations laid, the technology developed, the first missions launched. You'll watch humanity take the initial steps towards spreading across the galaxy. And that might be enough. Knowing the journey continues, knowing someone will reach those distant shores, knowing humanity isn't confined to one world forever. The stars are waiting. The distances are vast. The journey is long, but it's already begun.